Hello. Anybody out there? Test. Okay, just checking that. Who's out there? Who's with me? Geometry. Hello. I am gonna do Geo first. I just made an announcement on Geo that I was live, and I'll make an announcement on Algebra 2 in just a wee bit. This is kind of a short lesson for Geo, so. If you're Geo, let me know. I know Amanda's Geo, right? Who else is Geo? Anybody else Geo out there? We got another. I'm gonna give it like maybe another minute for people to catch that notification that I went live. Hello, Uncle Bill. Are you really my uncle? So this time we're doing 3.1 for real. Last time I started the 3.1 notes, and I think it was it Carazal? I think that said, hey, aren't we supposed to be doing 2.3? I think that's who said that last time. Maybe not. So we got a small handful of viewers here, so I'm feeling good. I think we should start with that music at a reasonable volume. All right. So right about here, we are starting the replay. Welcome. Thanks for tuning in. Thanks for watching it live. We are doing 3.1 notes for geometry. And you know what, just for, the sake that everyone is watching at least this part, announcement wise, right? We have 2 weeks left. We have this week and next week of quarter one. We have a quiz on Wednesday, our normal C-Day quiz Wednesday. All of Unit 2 classwork for Geo is due on Wednesday. I told you that on Thursday/Friday, but just a reminder. And our quiz will be over the previous lesson, 2.3, and this lesson, 3.1. So let's take a look at 3.1. We're looking at transformations and specifically reflections. So a transformation is when we manipulate a figure or object or thing, whatever you want to call it, and rotate it or reflect it, flip it, make it bigger, make it smaller, or just simply scoot it left, right, up, down. All of those things are called transformations. So a transformation is a function that maps an original figure called this original, the before the transformation, is called the pre-image. And actually, let's go ahead and make my pencil a little skinnier there. That's called the pre-image onto a new figure called the image. So the before is pre and the after is just drop the pre. So there's the pre-image and the image, before and after. A transformation can change the position, it can change the shape, it can change the size, it can change just about anything, okay, of a figure. All of those things are considered transformations when we manipulate this figure. You can use function notation to express transformations like this. T of A equals A prime. So that reads as what I just said. So you've seen function notation when it comes to algebra stuff like f of x and g of x, right? Those were functions. We would look at them and go, oh, that's function f, or oh, that's function g, right? We're looking at GO right now. That's function f, that's function g. Well, this is a transformation. So T stands for the transformation, and the A represents the pre-image, and A prime represents the image. So that little prime means like, oh, this is the new thing. This is the after, all right? So before you do anything, you have figure A, B, C, and after you do something to it, you now have A prime, B prime, C prime. So that little apostrophe is called prime. So, rigid motion. A rigid motion is a transformation that changes the position of a figure without changing the shape or size. So that word rigid, hopefully we know what that word means, or at least somewhat. Rigid means firm, strong, unbreakable, harsh, right? So in this sense, when we are using the word rigid, we're meaning like unbreakable, unchangeable. So a rigid motion is something that only moves the object around, maybe a rotation, maybe a flip or something like that. But overall, like if it started as a triangle, it's going to end as a triangle. If it started as a small triangle, it's going to end as that same small triangle. It might be in a different spot, but nonetheless, you're going to look at that triangle and go, oh, that's the same triangle, okay? That is a rigid motion. So it's preserving everything, all right? You don't really need to super focus on these words, right? I mean, read them, right? Distance, angle measure, betweenness, collinearity. Preserving means to, not change, right? To make it stay the same, to preserve. Again, that word rigid, right? To be rigid means to preserve everything about the figure. The figures below show the pre-image ABC and the image A prime, B prime, C prime under a transformation. Determine whether transformation appears to be a rigid motion. So just a simple yes or no question. Is it rigid or is it not? And in this case, I hope you can see that basically the triangle's just been flipped a little bit, right? Or honestly, it actually is probably more of a rotation now that I take a second glance at it. And you know what? This note-taking app is going to allow me to do incredible stuff here today, folks. Incredible stuff here. I think I have a way of rotating, do I not? I thought I had... Yeah. You see that? Look at that. See? So when I rotate it, you can see that it's the exact same triangle. Now, granted, as I was rotating, I accidentally like made it a little bit bigger. But the point is it didn't get any bigger, right? I wish there's got to be a way for me to rotate without changing the size, but we're not going to sit here and fiddle with that. But the point is it was simply a rotation, but it was rigid, okay? We did not change the shape of that triangle. We did not change the size of that triangle. It's the exact same triangle. It just happens to be upside down now. Look at this one, though. Clearly, the bottom has been stretched out a lot. These are quite obviously not the same triangle in any way, right? That's a really sloppy does not equal sign, all right? But these are clearly not the same triangle, so not rigid. It was stretched. And again here, not rigid. We gotta, thinking about these words up here, preserves distance, meaning same size, right? The sides of the triangle are all the same length if it's been rigid, but clearly this triangle is a little bit bigger now than this one right next to it, so it's not rigid. So an example of a rigid motion is a reflection, right? When you look at yourself in the mirror, your eyeballs aren't abnormally larger compared to them in real life. Your hand is the same size. You can put your hand right up to the mirror and your hand's gonna match up with your hand, right? A reflection is a rigid motion. Everything looks the same. It's just been flipped around, right? But nonetheless, it's you in that mirror. And nonetheless, when we reflect an object, it's still the same object. Okay, so a reflection is a flip over a line called the line of reflection. No surprises there. Each point and its image are the same distance from the line of reflection. We can use blank to describe how a pre-image transforms. Function notation. Sorry, I was trying to remember what I wanted my blank to be. Transformation. Let's call it transformation notation. My apologies. We can use transformation notation to describe how a pre-image transforms. Look here. Look at this. So again, this idea of function notation. What exactly am I looking at here? This is transformation notation, and it has all this information in it that's really valuable to us. When I look at this, what are the things that it tells me? Number one, it tells me, hey, you are reflecting. That little r stands for reflection. Okay, well then, what is this? What is this y right next to it? Y equals 0. That represents the line of reflection. What is this right here? That is the pre-image. That's the before, right? So what am I telling you to do? I'm telling you, hey person, hey student, reflect this point over this line. That's what that is. It's like a command. It's directions. It's an objective that says reflect this point over this line. That's what it says. And what is this right here? And the answer is the image. Okay? Reflect this point, the pre-image, over this line, and you get this answer, the image. So over here, you can see the line of reflection is right here, and we're starting out with this pre-image here, and when it gets reflected across this line, we end up with this image here. And how do I know that the purple one was the pre-image and the blue one was the image? Because the primes, okay? So right here are some right here are some simple, quick rules on how to reflect. Okay, so to help you imagine that the line y equals 0 is the x-axis. Okay, so a super quick sketch here. I'm going to erase. I'll try to make room for each of these. So the line of reflection is the x-axis. Okay, I can zoom in. The line of reflection is the x-axis. So if I have a point over here, then it's going to get reflected down here, right? Flip of the page. So what's happening is the x part is staying the same and the y value is getting flipped. Do you realize that? Do you see that? Because I really want you to see that, right? The x value is the same, but as it gets flipped across, instead of being up here at, let's say, +3, it's now down here at -3. So that's why the y value has been flipped. The x value stays the same, but the y value changes. So for example, when you reflect the point 2, 5, it becomes 2, -5. Let's imagine this again, except with the y-axis. So here's our coordinate plane, and there's the line of reflection. Let's say a point is right here. When it flips across, it's going over to this side. And what's happening there? The y value is staying the same as it flips across, but the x value is clearly changing, flipping to the other side. So that's why this time around the x value has been flipped, but the y value stayed the same. And this becomes, I'm flipping the -4 and becoming a +4, but the y value stays the same. And then the last one, we're flipping over the line y equals x, which looks like this. And what happens here is when we have a coordinate up here and a coordinate then and results down here, the x and the y values are flipping, okay? So let me help you see that. We had a negative x value over here. Now we have a positive x value. The y is now negative, right? Because we went down. So we had a negative x value. Now we have a negative y value. We had a positive y value. Now we have a yeah, sorry. I sort of confused myself there for 1 second. Let me say that again, because in case you got confused. There's a positive or negative x value right here. Now it's become a negative y value. There was a positive y value. Now it's become a positive x value. So they're just switching places. They're just switching places. So this becomes -2, 9. They just flip-flopped. These rules are your friend, right? You want these like basically at all times while doing the assignment, okay? These make life so much easier to have these rules, okay? So if I had to make up one more example here of each just to nail it in for you. So I'm going to write tiny underneath. What if I gave you the point 37, the point -3.5, and the point -4.2? Well, what does the rule say? Keep x the same, but make y negative. So 3, -7. What does the rule say? Flip the x value, keep y the same. So this negative does not mean slap a negative sign on it. It means flip the value. So it was negative. Now it's positive. And 5 stays the same. And this right here says switch x and y. So now this becomes 2, -4. Is reflection a rigid motion? Yes, of course. I already discussed that. So if we were in a physical classroom, I'd give you some tracing paper and we'd physically do this, okay? But that's not where we are, so we're skipping this. Oh, here's a couple more examples. I guess I didn't need to make one up. So you need to read this notation and realize, okay, which thing am I doing? I'm reflecting across the x-axis. And do we realize that? Let me pull something up real quick. Let me pull something up. So the line y equals 0 is this flat horizontal line, right? We need to realize that, okay? Because it needs to be more than just letters on a page. It needs to be something visual to you, especially when we look at a graph. When it says we're reflecting over the line y equals 0, what we're saying is, okay, if I give you a random point, say right there, the reflection is going to reflect across the line y equals 0, which is the x-axis, the horizontal axis. So it's going to flip downwards here. So it's currently 1, 2, 3, 4, 5 above. Now it's going to be down here, 5 below when it gets reflected, which is why, oh, the y value gets flipped, right? Instead of being up here positive, it's now down here negative. Which is exactly what's happening to this point right here. Instead of being up at positive 25, it's now going to be reflected down to negative 25. All right, look at this line. X equals 0 is the vertical line, the y-axis. So now when I reflect this point, this blue point, it's going to get reflected across. So instead of being 1, 2 to the right, it's going to be 1, 2 to the left as it gets reflected. So what's changing? The x value. The y value is staying the same, but the x value has now been flipped as we move that across, okay? So that's why the rule is change the x value. So now it's going to be at negative 22, but the y value is still the same. This is another vertical axis. So once again, the x value flips, but the y value stays the same. And then the last one, y equals x. We're almost done here. Y equals x, you can see, is the diagonal line. So I didn't mean to delete both points. Let me bring that guy back. 2, 5. When I reflect the point 2, 5 across the line here, it's going to go, directly across. And where does it go? The x and y values flip. Instead of 2, 5, it's now at 5, 2. You can see it's directly across. So looking at this guy, these two are simply going to flip places. These are super quick and easy. I mean, especially if you've printed out the notes and you're following along with me, you can do this super physically and really manipulate it and have a good idea of what's happening here. So it says reflect over the y-axis. The y-axis is this guy here. So I'm reflecting over this axis. And when we reflect, everything's just going on the other side. And the words that I used up here, just to recall, each point and its image are the same distance from the line of reflection. So what does that mean? This point right here, we'll call it A prime, or sorry, not A prime, we'll call it A, is 1, 2, 3 away from the line of reflection. So that means the image needs to be 1, 2, 3 away on the other side. A prime, we'll call this B. It was 1, 2 away, so this one's 1, 2 away. This is C, which is 1, 2, 3 away. So the other guy's going to be 1, 2, 3 away. It's really that simple. Like, do not overcomplicate this, right? We all know what a reflection is. We see it in the mirror every day. It's just like a carbon copy, but flipped. All right, I'm moving quick because I don't see a point in dilly-dallying on this. The x-axis, you need to realize that this is the x-axis. So here's our line of reflection. And I'm having the exact same thought. This point is 1, 2, 3, 4 away. So up 1, 2, 3, 4. These are both 2 away. 1, 2. So up 1, 2, up 1, 2. 1, 2, 3, 4 again. 4 on the other side. Let me plot them super quick. 1, 2, 3, 4. 1, 2, 1, 2, 1, 2, 3, 4. If you got a question in the chat, let me know. Let me point something out here. You know, actually, let me just erase what I just drew. Technically, there's a point right here, right? And there's a point right here. Where are they going? Well, they're on the line of reflection. It's like a hinge, right? It's like a door hinge, right? The entire door moves except for essentially, I know the hinge moves a little bit, obviously, but like the hinge is staying in put, right? It's freaking screwed into your wall. It's not moving that much, right? It's turning, but its position is the same. So think of the same thing when you're imagining this object flipping upwards, right? It's on the bottom half of the graph and now it's going to flip upwards. Those 2 points that are on their line of reflection are like the hinge as it's turning. Those 2 points are going to stay in place while the rest, this guy, this guy, this guy, and this guy are all going to reflect upwards. E and F, I'll call them, they're staying put though. They are the hinges. One more time, the line of reflection this time is y equals x, which is a diagonal line with a slope of 1. Right, I'm going up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. That's how I know how to draw that line. And when these guys flip, this is slightly less visual, right? You might get off a little bit. And that's why I would encourage you to remember the rule that the x and y values flip-flop. So A is at point -1, 1. So when it flips across, it's going to go to 1, -1 right there. And you might have seen that visually, but do you see exactly where B should go, right? Does it go here? Does it go there? Does it go out here, right? I mean, you tell me whether you know exactly where it goes, but I'm not going to risk it. That B is at -3, 2. So when I flip, it's going to go to 2, -3. 1, 2, down 1, 2, 3. Did you guess that it was going to be there? Did you know it was going to be there? I don't want to guess. I want to know. And then C is at -2, 3. So when that flips, it goes to 3, -2, which is right there. No, it's not. -2, right there. Beautiful. If you saw that, great. If you didn't, right, what did I just do here? I simply applied the rule that we learned above. And I could have done that to any of these points, right? Like, don't get me wrong. Let me just do one for example. This point A is at 1, 2, 1, 2, 3, 4. -2, -4. And what's the rule from above? If you don't recall, and again, I would have these super handy as you do the classwork. What's the rule from above here? When we flip across the x-axis, you flip the y value. So this becomes -2, +4. Well, that's exactly where we went, right? That's exactly where we plotted the point. All right. One more page, one more quick practice. Those of you watching the replay with me still, those of you watching live, I understand that everything's on a screen. We don't have a physical piece of paper to like manipulate with our pencil, and kind of it is a slightly more challenging, but I encourage you, make your screen, put some fingerprints on your screen, touch it, count on the coordinate plane, right? Think about, you might have, if you have some graph paper, you might do a quick XY axis sketch, that sort of thing, and plot it yourself. It might take a little bit longer, but it'll pay off, because just staring at the screen might not be enough, So I encourage you to put some fingerprints on your screen, get a graph paper, something like that. So perform the following transformation. I like these because we're introducing something different here. We're introducing this line x equals 2. I have some questions in the classwork, and maybe I should have said this before, because maybe I've lost some people at this point on the replay, but there's x equals a number and y equals a number, right? Which is which? Well, and